Okay, so welcome to 1.6, which is the absolute or absolute value functions. Absolute value functions. And we remember that the absolute value has a graph that looks like a V, right? So let's recall. That if we have f of x being equal to the absolute value of x, then its graph is, let's do a little x and y coordinate axes, x and y. So it's going to be a v with a slope of 1 and -1 from the origin. So this is the graph of absolute x. Okay, actually let me move this down a bit. Maybe to there. Okay, so given that, let's consider that graph. So consider. But I'm going to look at two parts of that graph where they meet at the point. So once again, x and y coordinate axes. X and y. So 1, 2, 3. 1, 2, 3. 1, 2, 3. 1, 2, 3. Okay. So let's look at the right side. Let's say we've got the absolute value 0, 0. The absolute value of 1 is 1. The absolute value of 2 is 2. The absolute value of 3 is 3, etc. So what if I were to continue this line to the left? This would be the line y is equal to 1 times x, because the slope is 1, if I were to continue that. Similarly, let's look at the other part of the absolute value function. Let's say it's open here at 0. The absolute value of -1 is 1. The absolute value of -2 is positive 2. The absolute value of -3 is positive 3, etc. And if I were to continue this all the way to the right, this would be the graph of y is equal to -x. So let me actually need to give myself a little bit more room here. So this purple is a graph of y is equal to -x because it's got a slope of -1. So notice where I don't have the dashed lines, where they're solid lines, that is the graph of the absolute value function. So I noticed that, well, actually, I hope you can see that. Maybe I should erase this a bit more. Don't want you to get confused. That is not on the graph. Okay, so what I'm saying here is that we can express the absolute value function as follows. The absolute value function is really two functions. It's the function y equals x, provided that my values along the x-axis are, say, greater than or equal to 0. Or it's the function y is equal to -x when I'm looking at values on the x-axis strictly to the left of 0. Okay, so let's define now the absolute value function formally as a piecewise defined function. So definition. So the absolute value function, that's what we're defining, the absolute value function. Don't think it's hyphenated, is it? Oh, I don't know. It's too late. The absolute value function. That's what we're defining. The absolute value function is the piecewise defined function. Is the piecewise. I before E except after C. Hopefully I spelled piecewise correctly. It's a piecewise defined function. Given by the absolute, let's call it f of x being equal to the absolute value of x can be written as, let me move this down a bit, either x, when my values of x on the x-axis are greater than or equal to 0, or it's negative x when my values on the x-axis are less than 0. Okay, so for example, so let's use transformations. So use transformations, formations, to plot the following. Plot the following absolute value functions. Following absolute value functions. Okay, so number one, let's say we just have the standard function. F of x is equal to the absolute value of x. Okay, if we have that f of x is just the absolute value of x, that's pretty straightforward. So x and y coordinate axes. We'll just do a small little graph here because we know what it looks like. X and y. So 1, 2, 1, 2, 1, 2. So I know the absolute value of 0 is 0, the absolute value of 1 is 1, the absolute value of 2 is 2. So to the right, I go up at a slope of 1. To the left, the absolute value of negative 1 is positive 1. The absolute value of negative 2 is positive 2. So I have this V-shaped graph for my absolute value. So this is the absolute value of x, which hopefully we know really well by now. So number 2, let's plot the graph of f of x being equal to 2 times the absolute value of x. Let's do this in purple. So now f of x is 2 times the absolute value of x. So that means it's twice as tall, right? So 2 times as tall. Okay, so what I can do, let's look at our x and y coordinate axes again. X and y. So 1, 2, 3, 4. 1, 2, 1, 2. So before we just had the v. So this would just be the original absolute value of x. It was just the v shape. With points at 0, 1, and 2, say. So now what I want to do with those points is make that graph twice as tall. Now remember, you don't have to plot this graph. I'm just trying to show you where I'm getting this from. So twice 0 is 0. 2 times 1 is 1. 2 times 2 is 4. So it'll be thinner, a taller, thinner graph. 2 times 1 is 1, and 2 times 2 is 4. So it's going to be a taller, thinner graph. So this is 2 times the absolute value of x. Still a v, but twice as tall. So So now let's look at number 3. Let's do that f of x is equal to 2 times the quantity x plus 3. Okay, so we have that f of x is equal to, we still have this 2, but now we have the quantity x plus, what color shall I use? Let's use green, 3. Okay, so what does this mean? I know it's twice as tall because of the 2, so 2 times as tall. And the green now, the plus 3 inside the absolute value, means left 3 because it's counterintuitive. But what's interesting is it's 2 times as tall and left 3. But look, the graph I did beforehand is also 2 times as tall. So why don't I just take the graph I've got right above here, this purple guy, x and y, 1, 2, 3, 4, 1, 2, 3, 4, 5, 1, 2. So I had this purple guy here that was twice as tall already. But now I'm shifting that left 3 units. So let's do 0 goes left 3, so that's negative 3. This point here at 1, 2 goes left 1, 2, 3. This point here at 2, 4 goes left 1, 2, 3. So I get this, and similarly, the points on the left also go left 3. So this is now 2 times the absolute value of x plus 3. Still with me so far? So I had absolute value of x, which I then made twice as tall, which I then moved 3 units left. Okay, let's do a couple more. Number 4, let's consider f of x is equal to negative 2 times the quantity absolute x plus 3. Okay, so what color should I use for this graph? Have I used... Let's use a dark yellow. So I have f of x will be equal to, now I've got a negative in front, negative 2 times the quantity x plus 3 . Okay, so now the negative is an x-axis reflection. So x-axis reflection. I know that the 2, let's see if I can draw that a bit better. Nope, I guess I can't. Okay, so this 2 here is 2 times as tall. And we already know that this plus 3 is left 3. Okay, so it looks like all I'm doing to the graph above is reflecting it across the x-axis. So let's go ahead and draw this. So let's see, what do we have? X and y. So 1, 2, 3, 4. 1, 2, 3, 4. And 1, 2, 3, 4, 5. Okay, so we had the pink graph, which was to the left 3 and twice as tall. now all I'm doing to change that is I'm reflecting it about the x-axis. So because of this hot pink negative, I'm going to reflect about the x-axis, which means it's just going to go downhill. It's going to be like a mirror image, as if this were water and it were reflecting. Oops. Okay, so this down here would be the graph of negative 2 times the quantity x plus 3. Yeah, put that there. Okay, let's do one more for good measure. What have I not done yet? Vertical translation. Okay, so number 5. Let's say that f of x is equal to negative 2 times the quantity x plus 3, to which I'm adding 4. What color should I do? I have not done a green graph. Okay. But green is reserved. Oh well. I'll do a dark green graph. How about that? Okay, so we have that f of x is equal to minus 2 times the quantity x plus light green 3. And now I've got the addition of 4. So I know the minus is an x-axis reflection. I know that the plus 3, sorry, I've missed the 2. The 2 is twice as tall times as tall. I know that the plus 3 is counterintuitive, so that's left 3, but now I have a lonely 4. And since it's on the outside, it's up 4. Okay, so all I've done to change from part 4 to part 5 is add 4. So I claim that it's going to look just like the graph above it. Pardon me. So we went like so. X and Y. So 1, 2, 3, 4. 1, 2, 3, 4, 5. 1, 2, 3. So we had the graph right before it, which looked like so. No, that's terrible. Trying to do this as best as I can. Not succeeding very well. So this is the graph we had in the problem before. And how am I changing this graph? I'm shifting it up 4 units. So that's what the plus 4 does. So 1, 2, 3, 4. So everything gets shifted up 4 units. And there we are. So this green graph will be given by negative 2 times the absolute value of x plus 3, to which we're adding 4. Okay, so that was fun. Look at all of that. It's basically all the same graph. We're just doing a whole bunch of transformations to it. Okay, so let's note something. Note. So for all values of x less than or equal to 0, this implies that the absolute value of x is greater than or equal to 0, right? Because the absolute value of a negative number is positive. So therefore, the absolute value of a negative number, say negative 5, will be the same as the absolute value of the positive number. Say positive 5. In absolute value, they're both the same. It's a theorem. Okay, so let's let A be an expression in X. Then, if we have that the absolute value of A is equal to some positive real number B, then this implies that A is either the negative of B or A is just the same as B. Okay, well, let's note something. If f of x is equal to some absolute value of an expression A minus a constant B, we set f of x to 0 to solve for x. Okay, so what do I mean by that? Let's see some examples. So for example, let's solve the following absolute value. Solve the following. Absolute value equations. So number 1, let's say we have that 0 is equal to the absolute value of 2x minus 3 minus 1. Okay, so that's our function. So we have 0 is equal to absolute value of 2x minus 3 minus 1. So we're going to add 1 to both sides. So this gives us 1 is equal to the absolute value of 2x minus 3. Actually, do you know what I'm going to do? I'll put that underneath, because now I will use my indication or my implication. So, do you agree that whatever's inside in absolute value has to be 1? So we either have that it's negative or we have that it's positive 1, because the absolute value of negative 1 is 1 and the absolute value of positive 1 is 1. So now we can just solve in each case. So I'll add 3. So what do I get here? I get 2x is equal to 2, or x is equal to 1 in this case. If I add 3 over here, I get 2x is equal to 4, or x is equal to 2. So the solution set here is x is equal to either 1 or 2. Okay. Do I have enough room to put another one here? Maybe I do if I don't skip a line here. Trying to save space. Electronic paper. Okay, so let's see if I can force another one here. So number 2, let's say we have the equation 0 is equal to negative of the absolute value of 3x plus 5 plus 7. So in this case, if we have 0 is equal to negative the absolute value of 3x plus 5 plus 7, I'm going to add the absolute value to each side. So the absolute value of 3x plus 5 will be equal to 7. So what this means is that must mean that what's inside that 3x plus 7, that 3x plus 5, is either negative 7 or what's inside 3x plus 5 is positive 7, because I know that the absolute value of negative 7 is the same as the absolute value of positive 7. So let's go ahead and subtract 5. So that's negative 12, and divide by 3, that's negative 4. Once again, we'll subtract 5, so that's 2, divide by 3, that's 2/3. So over here, the solution set will be negative 4 and 2/3. Okay, so let's do another one. And I just barely fit that on there. So number 3. And the final one for this one, let's do 0 is equal to 4 times the quantity, x plus 2 minus 12. Okay, so what do we have? We have 0 is equal to 4 times the absolute value of x plus 2 minus 12, which means that 12 is equal to 4 times the absolute value of x plus 2. Dividing by 4, we get that 3 is equal to the absolute value of x plus 2. Okay, so what that means is what's inside that x plus 2 is either negative 3, or what's inside will be positive 3, because I know that the absolute value of negative 3 is the same as the absolute value of positive 3. Subtracting 2, I get that x is either negative 5 or x is 1. So there we are. That is our solution. We get that x is either negative 5 or 1. Okay, so let's consider the following. How about the graph of just the regular absolute x? So x and y coordinate axes, let's go ahead and do it here. X and y. Let's have just some random number a here. So I know that the graph is v. It's a v shape. And I know that the x and y values correspond in absolute value because it is an absolute value. So what that means is if I look over here to where this point is going to be a, comma a, because the absolute value of a is a. And similarly, if I look over here, the coordinate here is actually going to be negative a, because this is negative values for x. So this is actually negative a, comma a. Okay, so let's consider, actually maybe I should do that here. Let's consider, make that a bit smaller. Let's see how small that is. Yeah, let's consider this region here and here. So these are values. Actually, no, let's consider these values of y. Okay, so I want the values of y, or the function, to be less than or equal to a. So I want that this function, the absolute value of x, is strictly less than a. So where is that going to be true? If I look at the x-axis, for which values of x is that going to be true? Well, I claim that that's true for values of x between negative a and a. So the way I'm going to say this is that is the right, is that negative a will be less than whatever x is, and x will be less than a. Or a preferred way would be, this implies that x is between, so is an element of, the interval from negative a to a, which is a more elegant notation, but either way is fine. Okay, now what if I'm concerned with values of y that are larger than a? Actually, maybe I should use a different color. Oh boy, I can do this. Okay, so if I want to look at values that are larger, do you agree that I would have to go out to these regions on the graph? Well, those regions correspond to values of x that are either to the right of positive a or to the left of negative a. Agreed? Actually, let me color code. I would like to color code this. No. Can I? I guess. Nope. I'm going to have to erase it. So I would prefer to have these a different color. Maybe. Yeah, that's better. Not so harsh. I don't like that red. There we go. Much prettier. Okay. So if I want that the absolute value of x is greater than a on the y-axis, then this implies either that x is to the left of negative a, or x is to the right of positive a. More succinctly, well, no, actually, I like that way. That suffices. Okay, so hopefully this graph makes sense. So I'll give you a theorem instead. So theorem, which explains this. If you don't understand the picture, we can just use the theorem, but hopefully you're getting the picture. That would be nice. Okay, so let's let a be an expression in x. So be an expression in x, and be a positive real number. So notice what I say versus what I write. B greater than 0 is an element of the real numbers. That's how we say in math, b is a positive real number. Okay, so then what do we have? So number 1, if the absolute value of a is strictly less than b, this implies that negative b is less than a, which is less than b. So that would correspond to this first case, if I'm looking at values less than a, right? Or less than b in this case. Okay, so number 2, I guess I shouldn't have swapped the letters. Let's say the absolute value of my algebraic expression is less than or equal to b. It's the same inequality. It's just negative b is less than or equal to a is less than or equal to b. So similarly with the greater thans, if we have the absolute value of a is strictly larger than b, then this implies A is either to the left of negative b, or A is to the right of positive b, like we had up here, right? Similarly, with the non-strict equality, greater than or equal to, then this implies A will be less than or equal to negative b, or A will be greater than or equal to b. Okay, so let's note something about these. These two are small, little intervals for less than. So let me do little intervals for less than. So these are less than inequalities, and these are little intervals. Okay, they can be contained within a little expression like this. However, these two guys are large, infinite intervals. So they go off towards the infinities. Do you agree that here and here I'm going off towards negative infinity and positive infinities? So large, we can think of large as infinite, or large and infinite go together. I'll just underline those two, because if it's greater than, so greater than. So if we use greater than, I must go off towards both infinities. If I use less than, I must have a small little interval. So remember, greater than goes off towards the infinites. So let's note something. Note. So you'll notice I changed the notation. We have the inequality notation and the interval notation. I'm going to deal right now with the inequality notation. So we can set up both three-way inequalities as A less than, that's negative B. Negative B less than A less than B for the first case. Negative B less than or equal to A less than or equal to B for the second case. But we can also do negative B greater than A, which is the same thing as A less than B, and that A greater than B. So we've got the A less than negative B and A greater than B in one inequality, or one three-way inequality rather. So negative B is greater than or equal to A, which means A is less than or equal to negative B, and then A is greater than or equal to B. So what we can do with these two guys here, can separate into two intervals after solving for x. So what do I mean by that? Well, let's first solve some inequalities graphically, absolute value inequalities. So, for example, pardon me, solve the following. I thought I was going to cough. I didn't, so solve the following. Absolute value inequalities. Do I have enough room? Barely. So solve the following. Absolute value inequalities graphically, meaning plot the graph. Okay, so number one, let's say we have 3 minus the absolute value of x plus 2 is strictly larger than 0. Okay, so I'm going to color code this as plus 3, then minus the absolute value of x plus 2 is strictly greater than 0. Okay, so to plot this, I claim that this will be up 3 because it's a positive 3. I claim that this will be an x-axis reflection. I claim that that plus 2 inside will be left 2. Okay, so let's go ahead and plot. There's no dilation, which is good. So x and y coordinate axes. X and y. So 1, 2, 3, 4, 5, 6. 1, 2, 3. 1, 2, 3, 4, 5. Okay, so I know that normally the absolute value graph is a V. But I'm doing a whole bunch of things to this V shape, aren't I? In fact, I probably need to leave myself a little bit more down here. I'm only going up 3. Okay, so I'm going left 2, reflecting about the x-axis, and then up 3. So left 2, reflecting about the x-axis means I would open downwards, and then I'm going up 3. So I claim when all is said and done, we're going to get a graph that looks like so. I claim that that has been shifted left 2, reflected about the x-axis, and then shifted up 3 units. So hopefully at this point you'll understand the intermediate steps that I didn't explicitly show. But now I want to look for values where this is greater than 0. So it can't be equal to 0, so the y value cannot be equal to 0. But I want the y value to be greater than 0. So I claim that it's greater than 0 for values of x between where? Well, let's see, that was negative 1, 2, 3, 4. Oops, wrong tool. Negative 5 and 1. So I claim that the solution set will be the interval. So x will be between negative 5 and 1, non-inclusive because there's no equal, it's just greater than. Okay, so notice this is interesting. I thought greater than went off towards the infinite. And the whole reason we've got an issue here is because of this negative. And we'll get to that in a moment. So actually this is correct. So now let's do another one. So number 2, actually let me move this up a bit. So number 2, let's do 2 times the absolute value of x minus 3, from which we're subtracting 4 is less than or equal to 0. Okay, so I have 2 times the absolute value of x minus 3 I'm then subtracting 4, and I want that to be less than or equal to, actually, wrong color, less than or equal to 0. Okay, so what does this 2 do when it's multiplied in front? So 2 times as tall. Inside the absolute value, I have a negative 3, so that's right 3 because it's counterintuitive. Outside the absolute value, I have a minus 4. So that is intuitive, so that's down 4. Okay, so what do we have? Let's go ahead and plot this. So x and y coordinate axes. Oh, going right 3. So I should maybe put this over. Oh, why is this not working? Come on. Put this over here. Something like so. So x and y. No, maybe I should have moved it over a bit. Okay. So normally my absolute value would look something like so. But I'm shifting this graph where I'm making him twice as tall. Then I'm going to shift him to the right 3 and down 4. So twice as tall to the right 3. Oh, I didn't put markers on my graph. 1, 2, 3, 4, 5. Oops. 1, 2, 3. 1, 2, 3, 4. So we have to the right 3, down 4, 1, 2, 3, 4, twice as tall. Okay, so now I claim that we're going to get a twice as tall V shape that looks something like so, and you can verify this for yourselves. Okay, so 1, 2, 3, 4, 5. Well, that's interesting. Okay, so I'm looking for solid dot can be 0, and then I want everything less than or equal to 0. So less than or equal to 0 for y would correspond to down here. And those values for x, for x include the points 1 and 5, but do not include the points beyond it on either side. So it'll be 1 to 5 and nothing beyond it, and that does work with the less than. Okay, let's do another one. Number 3. So what did I do for number 3? Let's see. So negative 2 plus the absolute value of x minus 1 is strictly larger than 0. Okay, so I have negative 2 plus the absolute value of x minus 1 is strictly larger than, I'll use yellow, is strictly larger than 0. Okay, so that negative 2 has nothing, it's not attached to the absolute value. So I know that that just means down, up or down. So down 2. The negative 1 inside the absolute value means right 1. And that's really all we have. So down 2 and right 1. So x and y coordinate axes. X and y. 1, 2, 3, 4, 5. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3. Okay. So I know that my normal absolute value function is this V-shaped guy here. Now remember, you don't have to show me this. I'm just showing you this so you'll understand. So I'm going to transform this. I'm going to move him first to the right 1 and then down 2. And then just draw the function. Same function. No, it's not taller, nor is it shorter. No dilations. Okay. So what I'm looking for now is where that this is strictly larger. So open dot, no equal sign. And I want it to be larger than 0. So my values for y are larger than 0. Well, those correspond to values for x that are to the right and to the left of the intercepts. And what values of x were those? Negative 1 and 1, 2, 3, positive 3. So I claim that from left to right, x will be between minus infinity to negative 1, non-inclusive, or between 3 and positive infinity. So number 4. Let's do 6 minus 3 times the absolute value of x plus 2 is less than or equal to 0. Okay, so this is a positive 6. This is a negative 3 times the absolute value of x plus 2 is less than or equal to 0. Okay, so what do we have here? The plus 6 on the outside is up 6. The minus sign attached to the absolute value will be x-axis reflection. I know that the 3 will be 3 times as tall. I know that the plus 2 inside will be left 2. Okay, so we've got a lot going on here. So x and y coordinate axes need to go up 6 units. One, 2, 3, 4, 5, 6. 1, 2, 3, 4. 1, 2, 1, 2, 3, 4, 5, 6. So x and y. So my normal graph is this V. Okay, so what am I doing with this V? I'll I'll look at my horizontal and vertical translations first. So I'm going left 2, and then up 6. 1, 2, 3, 4, 5, 6. But it's reflecting about the x-axis, meaning it opens down, and it's 3 times as tall. So it opens down, and it has a slope of 3. So this is going to be a very thin absolute value because it's 3 times as tall. Okay, so we have less than or equal to, so we can have solid dots. And I want that my values for y are less than or equal to 0, so that would be down here and down here. And those correspond to values of x to the right forever and to the left forever. Okay, so that would mean that x is between negative infinite and, what was this value? 1, 2, 3, negative 4, and that's 0. So, and negative 4, inclusive, it was a solid dot. So bracket, or start again solid at 0, all the way to the infinite. Okay, and you might be asking, why is it that this less than went off to the infinite, and this greater than was a small little interval, given what I said about little and less, and large and greater? Well, let's see. Why is that? So let's recall. So when multiplying or dividing, when multiplying or dividing, an inequality by a negative number, So we swap the inequality sign. So that is, i.e., id est. Let's say I have, let's use a is less than b. And let's say I multiply this by a negative 1. Well, this is going to give me negative a is greater than negative b. So not only do I distribute the negatives to a and b, I swap the signs. So notice this less than has become greater than. So swapped. Similarly, if I had a was greater than b, and I multiplied through by a negative or divided, doesn't matter, this would give me negative a is less than negative b. So once again, I will have swapped the inequality. Okay, so let's revisit some problems. So for example, solve the following absolute value inequalities. So solve the following absolute value inequalities algebraically. So this is where we're going to get our three-way inequalities. So if I have 3 minus the absolute value of x plus 2 is strictly greater than 0, let's go ahead and solve this. So 3 minus the absolute value of x plus 2 is strictly greater than 0. So the first thing I want to do is I want to subtract 3. So I get minus the absolute value of x plus 2 is strictly greater than negative 3. But now I'm going to go ahead and I'm going to multiply this inequality by a negative 1. So what's going to happen now is I'll get the absolute value of x plus 2. I have to swap the inequality now. So this will be less than positive 3. So I made each side the negative of what it was, but I swapped the inequality because I multiplied by a negative. Okay, so here's where we can, what color should I use? Purple. So once we have the inequality isolated, we can put negative 3 with the inequality on the left, same inequality. Then without absolute values, I put x plus 2, keep the inequality again the same, and put positive 3 on the right. So this is what a three-way inequality is. I keep the inequality the same, put the negative constant on the left, positive constant on the right, and put what's inside the inequality, the absolute values in the middle. So now we solve for x, meaning we subtract 2 from all three sides. So we get negative 5 is less than x, and x is less than 1. Okay, so less than means little. So the way we can write this is x is on the interval from negative 5 to 1, non-inclusive. Okay, well that's interesting, because if I look at this problem, it's this same problem, and we did get the same value when we looked at it graphically as when we did it algebraically. Okay, so number 2, let's say we have 2 times the absolute value of x minus 3 minus 4 is less than or equal to 0. Okay, so we have 2 times the absolute value of x minus 3, from which we're subtracting 4 is less than or equal to 0. Let's add 4. So 2 times the absolute value of x minus 3 is less than or equal to 4. Now let's divide by 2. Now 2 is not negative, so we just keep the inequality the same. So once we're here, there's no negatives, no need to worry. We can put the negative of 2 on the left, keep the inequality the same, put what's inside the absolute value in the middle, keep the inequality the same, and put the positive absolute value on the right. Actually, I think I'll change these colors just so that we can see them. It's easier to see that way. Okay, so now let's add 3 to all three sides. And that will give us what? That'll give us that 1 is less than or equal to x, which is less than or equal to 5. so once again, these are less thans. So the way we would rewrite little less than symbols is that x is between, because of the equal signs, 1 and 5. Brackets. Okay, now this should look familiar because it is also what we got for this problem up here graphically. Okay, let's do number 3. Go to the next page for this. Okay, so let's see, which one did I do there? Okay, so let's do -2 plus the absolute value of x minus 1 is strictly larger than 0. So -2 plus the absolute value of x minus 1 is greater than 0. Let's add 2 to both sides. So x minus 1 is greater than 2. And we're done now. We've isolated the absolute value. So we can rewrite this as negative of 2 on the left. I'll keep the absolute value the same, is greater than x in the middle, and x in the middle is greater than positive 2 on the right. Okay, well, I'm done. But let's notice we have two things going on here. We have x is less than -2. So x is less than -2, which is the same thing as -2 being greater than x. And then up here we have x is greater than 2. So the way we would write these two intervals is x is between the green interval. If x is less than -2, that's from -infinite to -2. Union the gold interval. If x is larger than 2, that would be from 2 to the infinite. And notice that is what we got. Oh, why do I have 3 there? Did I not add correctly? Oh, I forgot the +1, no wonder. Oh my goodness, wow. I just completely left it out. Okay, I was wondering why that was too easy. Because I forgot to write. Let me just cut this. I forgot to write -1 in the middle. Okay, that makes a difference. Okay, now that I've put the -1 back in, this will be different. I'll add 1 to all 3 sides. And now let's see what it really should be. Let's see if I get this right. Okay, so -1 on the left is greater than x now in the middle is greater than 3 on the right, and I believe that's what we had up there, but I'll check it in a moment. Okay, so once again, I'm going to say if -1 is if -1 is greater than whatever x is, then x is less than -1. Similarly here, x is larger than 3. Okay, so the solution would be x is between, well, x being less than -1 means it's everything to the left of -1, which is -infinite to -1. Or if x is greater than 3, that's from 3 to the infinite, all the way to the right. And we know that since it's a greater than, it should go off towards the infinites. Okay, let's see now if I got that one right. Up here, yes, -1 and +3. Okay, I did it right this time. I guess it was easier graphically. Okay, which it shouldn't be. It's always easier to just do algebra, in my opinion. Okay, so number 4 and the last one in this section 3:20, almost 3:30 a.m. I guess I should go to sleep. So we have 6 minus 3 times the absolute value of x plus 2 is less than or equal to 0. Okay, 6 minus 3 times the absolute value of x plus 2 is less than or equal to 0. Let's subtract 6 from both sides. So we'll get negative 3 times the absolute value of x plus 2 is less than or equal to negative 6. At this point, I'm going to multiply through by a negative. So now I'll get positive 3 times the absolute value of x plus 2 is, swap the sign, greater than or equal to positive 6. Let's divide by 3. So I get that x plus 2 will be greater than or equal to positive 2. So now I can rewrite this with a negative 2 on the left, a greater than or equal to what's inside the absolute value, x plus 2, let me not forget that this time, is greater than or equal to a positive 2 on the right. So we can subtract 2 from all three sides to solve for x. So we will get negative 4 is greater than or equal to x, which is greater than or equal to 0. Okay, so let's analyze this. If negative 4 is greater than or equal to whatever x is, that's the same thing as saying x is less than or equal to negative 4. And then on the right we have x is greater than or equal to 0. So the solution set should be x is between, so x is to the left of negative 4 infinitely, but I can actually get to 4, so square bracket, union, then x starts again. It can actually equal to 0, but it's everything to the right of 0. So notice once I isolated for the absolute value, I had a greater than, which means I go off towards the infinites. And let's see, is that what we got with when we did it graphically? 4 and 0, I actually did it correct. Okay, so there we are. I hope this is making sense, and I will see you guys in the next section.